I'm all the way back there at 1 more time. Wow. So 1 has 3 cube roots, 3 separate cube roots, 3 different numbers that are the cube root of 1. That's trippy, isn't it? That's trippy stuff, I think. Yeah. That's cool for me. I like that. I like that kind of stuff. Let's think about the 4th roots of 1. 4th roots are a little bit easier. I to the 4th power is going to be equal to -1 times -1. If I look at I to the 4th power, I go 1, 2, 3, 4. So I is a 4th root of 1. -1 is another 4th root of 1. You can think of -1 as being a 4th root of 1. Because -1 times -1 times -1 times -1. -I is another 4th root of 1. So, wait. 1 is a 4th root of itself, because 1 times 1 times 1 times 1 is 1. But there are 4 different 4th roots of 1. Similarly, there are 5 different 5th roots and 6 different... I think that's kind of sweet. I don't know. I love that stuff. I love that kind of spacey stuff. That's cool. Anyway. So, later when you take a class called modern algebra, you might run into the roots that are the roots of unity, they call them. Things called groups of the root that are the roots of unity. You'll stumble. Some of you will stumble upon that little fact again in your life. It's not just some freaky thing that House is doing once. Oh yeah, I promised you I'd talk about Euler. So let's do that. Euler discovered by taking the Taylor expansion of the cosine of theta, and those of you who haven't had calculus, don't worry about this. The Taylor expansion of the cosine of theta and the Taylor expansion of I times the sine of theta. And remembering that I squared is -1 and I to the 4th is +1, he found that the sum of these things works out to be the same thing as the Taylor expansion of e to the theta times I. E to the theta times I. So on your little handout that I gave you, you can see the Taylor expansions. It's on the back side. If you want to get John to teach you about that, hang on, page 253, and he will be happy to show you how that works. But what Euler showed, Euler is the second coolest mathematician ever. The only reason he's behind Gauss is because Gauss is only 1 letter off of House. But if it wasn't for that, he'd take your cake. But what Euler showed is that e to the I theta is equal to the cosine of theta times I to the sine of theta. Okay. In other words, it's another way of thinking about, it's another way of representing things in this angle form. We call this the polar form. If we take each of these things and multiply them by r, or let's go like this, we can kind of represent any point on the plane with that angle and that radius, that angle and that magnitude. Does that make sense? Now, unfortunately, we can't talk about 360 right now because the Taylor expansion requires us to use calculus. And so this works when theta is measured in radians, not when theta is measured in degrees. I don't know. Anyway, we have to go to radians here at this point. So just let's put this thing back down. And I want to ask you, where do you think e to the pi I should sit? just a little, for people that aren't familiar with radians, before you answer that question, some people already know the answer to that question. Before you answer that question, it turns out that if we take this circle and we think about the number of radiuses around the circle, there's one radius, it's going to take me 2 pi radiuses to get all the way around the circle. So an angle of 2 pi radians is an angle that takes 2 pi radiuses to go all the way around. If I take 2 pi and divide it in 4 equal pieces, 2 pi divided by 4 is equal to pi over 2. This angle is half a pi radiuses. Okay, so we have to talk about what e to the pi I would mean. What would e to the pi I be? Where would it be? What would the magnitude be?
R equal 1 according to that.
Okay, good. I'll trust that. Okay, so the magnitude would be 1. So it'd be somewhere on this circle here. And it says that if I plug in pi here, I'm plugging in pi here,
1, 0,
yeah, is it positive 1 or negative 1? Cosine of pi?
negative.
Cosine of pi is negative 1. So we got negative 1 plus 0. So you're telling me that if I let this angle, e to the theta I, if I let this angle be what we often think about as 180 degrees, but is equal to pi radians, if we let that angle be pi radians, e to the pi I is actually equal to negative 1. If we look at this Taylor expansion, and we think about this being pi, we end up with this thing here, let me get rid of the r's. We end up with this thing here being equal to negative 1. So there's the root, there's where this came from. There's where this idea comes from. This famous equation, e to the pi I plus 1 equals 0. This is Euler's famous equation, and a lot of people really think it's a cool equation because it puts e, pi, I, the addition sign, 1, the equal sign, and 0 all together. It puts all the coolest things together in one. It's like when you were in 5th grade and the kids picked their own teams. All the cool kids got together on one team. Remember that? You guys had a nicer school than we did. All right. So does that make sense? I was on the team with, square root of 1. All right. I think that's a cool result. How to explain where that comes from. The last thing I want to talk about is this thing called the Mandelbrot set. Mandelbrot set is a set of complex numbers. I just found out, this was only discovered in 1977. It was only found out in 1977, which for you guys is before you were born, many of you guys. For me, dang, I was a sentient being in 1977. I was alive and well and kicking. So the Mandelbrot set was not discovered very long ago.